We're going to look at number 5 in section 310, which is the notorious ladder problem, or a variation on that. Got this crazy, they draw this diagram. I didn't write all the words in the problem, but this is a ladder leaning against a side of a building or something. And, we're going to basically kind of put wheels at the top and bottom of this ladder so that it kind of a dumb thing, right? It's going to fall down, right? So this ladder's going to be in motion, and we're going to not have any friction or anything as we move, as the top of the ladder moves down the side of this house or structure, and as the bottom of it, moves along the floor away from that. Okay, so the information is supposed that the length of the ladder is 6.2 meters, and again, yours number might be a lot slightly different than this. That's the value of A, right? It's real important that the value of A is going to be 6.2 meters in this problem. And the top of that ladder, the top is sliding down the wall at a rate of 0.6 meters per second. Okay, so the top is moving down, right, this way at that rate. Calculate dx dt when h is 1.9. So what are they really saying? Find the rate of change of the bottom of the ladder as it moves, in this case, away from the wall, the instant that the ladder is h, right, is the height. The instant the ladder is 1.9, and I'm pretty sure they meant meters here. They didn't put that, but they should. The height is at that instant, the height of the ladder is 1.9 meters above the ground. Okay. And then give the answer to 3 decimal places. Okay, so what rate of change are we given? We're told that the top of the ladder is sliding down, right? And now the down is not so much important as the fact that h is that height. So as the top of the ladder slides down, the value of h is getting smaller. Because the value of h is getting smaller, it's decreasing, its derivative has to be negative. So dh dt has to be negative. You have to read the problem very carefully to know that. It's not going to say that the rate sliding down is a negative 0.6. It's going to say the rate of change is that. You have to be aware of this problem and realize if your quantity is getting smaller, that rate of change is negative. The quantity is getting bigger, then that's going to be a positive value. So for instance, when we look at x, this point, the bottom of the ladder is going to move to the right, making x bigger, right? It's going to get further from the wall. So we're expecting dx dt to be positive. If you get a negative value for dx dt, you know something is wrong. Okay, so we're going to find dx dt again when h is 1.9. So what's the equation that relates our variables of interest here? Remember, a is not a variable. It's 6.2 meters. It's a fixed quantity. So that's not, the ladder length is not changing. But clearly the variable or the equation that relates our variables of interest x and h is the Pythagorean theorem, right? X squared plus h squared is the hypotenuse, right? So this would be a 90-degree angle here, and the hypotenuse is the length of the ladder. So x squared plus h squared is, and I'm going to put not a squared, but 6.2 squared, because that's going to be some number. You can square that in your calculator. Now, that's our equation. We now need to find our related rates equation. We don't want to plug anything in yet. So I take the derivative with respect to t of both sides. Well, over here, this is a constant, 6.2 squared, some number. Derivative with respect to t is 0. The ladder length is not changing, so that's going to be 0. Over here, we've got a chain rule, right? X is a function of time. Notice this derivative with respect to time, derivative with respect to time. So it's the derivative of the outer function, x squared, which is 2x, times the derivative of the inner function, dx dt. Same thing here. H is also a function of time, right? The height of the ladder is changing over time. So chain rule, 2h times the derivative of the inner function, h dh dt. So we have that equal to 0. And we're looking for dx dt. So I'm going to solve for that. I'm going to, first of all, notice I can divide both sides by 2 just to clean things up, and that gets rid of that 2 there and there. And then I subtract the h dh dt that I'm left with, and then I divide both sides by x. Right? And there's my relationship. Now, notice in the problem I need to know dh dt, h, and x. Now I know dh dt, that's given, and I know what h will be, 1.9, but what about x? Well, at the instant h is 1.9, because we have this relationship here, right? I can plug in h is 1.9, and I can solve for x, right? Subtract 1.9 squared, and then take the square root. So that's going to be the value of x. Okay. And so let's plug in, right? dx dt when h is 1.9, I'm going to replace, don't forget we got a little minus sign here. H is 1.9, X we said was the square root of this. Whoops, that messed up there. That should be a minus sign there, times dHdt, which remember was negative 0.6. And that's going to be important because this negative and this negative will make this positive, making dx dt positive, which indeed it should be, as we discussed up here. All right. So we just evaluate this expression. And I've got it in my calculator here. I got rid of the negative signs. Negative times negative is positive. So I've got 1.96 times 0.6 divided by this whole quantity, 6.2 squared minus 1.9 squared. And so we wanted to round it to the third decimal place. The fourth decimal place is smaller than 5, right? So 1, so we leave this 3 the same, 0.193. And notice our units must be meters per second because that's the length units, right, are in meters and the time units are in seconds. Okay, so hopefully this is helpful on this one. Nice little ladder problem.